Welcome, friends. Uh, in this new lecture series of power system stability, here, uh, as we know, uh, the power system stability is one of the important topic of a power system analysis. So, if we see the outline of the entire previous lectures, then we have already studied the steady state stability, transient stability point. What do you mean by the dynamic stability? Stability limit, infinite burst operation. Then the synchronous generator connected to an infinite burst means here these are the two important topic. Infinite burst is basically it means what is the actual significance of the concept of the infinite burst into the network, and how we can replace the entire network with a infinite bus with a constant voltage and constant voltage magnitude and the 0 degree phasor angle of that voltage. Now the if your synchronous generator is connected to infinite bus, then how it will be, means we can calculate the maximum power value which is injected to the network by the synchronous generator. Then we have to study the power angle curve. This is basically a representation of a characteristics of changing into the power change of the power generated power with respect to load angle. Then afterward we have discussed the inertia constant and the swing equation, the role of inertia constant and the swing equation. This is it is basically an interrelation between the electrical and the mechanical power, or you can say the interrelation of the electromagnetic mechanical changing behavior of any machine with respect to swing equation. Then we have discussed the multi-machine model. If you have a multiple system into the network, then how we will get the equivalent swing equation, equivalent inertia constant for the entire multi-machine system. Then if the machines are swinging, or if a number of machines are connected with a network and they are swinging in the unison manner or the coherently, then how we can evaluate them, analyze the swing behavior of the entire system. So these are the topics we have already covered in our previous lecture, and it is already uploaded on my YouTube channel. You can download from there, you can view from there, and apart from that, the lecture notes are also available on the Google Classes. Now, today we are going to discuss the equal area criteria of power system, means power system stability. So, equal area criteria is nothing else. It is a basic, again, a one kind of analytical method, graphical analytical method by which we can analyze the system behavior. So, equal area criteria is basically the objective of studying the equal area criteria is the solving swing equation to determine determination of stability of single machine operating as a part of large power system. So if a machine is connected with a large power system, so the main objective of studying the equal area criteria is to solve a swing equation and determine the stability of the machine. Now, but before going to the in-depth in knowledge about the equal area criteria, we should be remember that the solving swing equation is not always necessary to investigate the system stability. If you want to investigate the stability of system for either steady state stability or transient state stability, so it is not required to solve every time the swing equation for any system. Only some cases direct approach is used to solve the swing equation. In some certain cases only we are using this method or the direct method to solve the swing equation. Now direct approach is based on equal area criteria, and this direct method is known as the equal area criteria. So equal area criteria method is not applicable every time for analyzing the stability of any power system network. It is uh, a graphical method. So if you go with for the computer programming of a graphical method, it is again become a complex task. So implementing the equal area criteria for analyzing the stability of any power system network is become a very tough task to means for monitoring the stability of the system. So Now, if we are talking about the equal area criteria, so from the swing equation we can see here, in swing equation md square delta upon dt square is equal to pi minus pe. So this is, we have already established this equation from the swing equation. Now we can represent pi minus pe as a pa. The entire system equation can be represented in a term of equation number 29. So now if we have to consider the two cases. One, an unstable system with the infinitely increasing delta with time and machine losses its synchronism. And second case, a stable system with oscillating delta and eventually die due to the damping. So stable system with oscillating delta and eventually die due to the damping of the system. So here we are going to discuss about the two different type of cases. One is case which is related to unstable system where the delta is continuously increasing infinitely, and with the time on the machine losses in synchronism, because system is unstable, so we can say the system loses its synchronism. And second case where the stable system is there and with oscillating delta and eventually die out due to the damping seal. So as you seen here in this figure, if we plot a curve for the load angle versus time, so this system represents a unstable system of case 1 where your load angle is infinitely increasing with respect to time. So it is not settled out a particular value, so we can say that this system is a unstable system. At the same time, in the second, here it is a oscillatory system, or where delta is oscillating with respect to time, and finally it will be a settle at a particular value. So this is known as a stable system. So from the swing coefficient criteria, d delta upon dt is equal to 0. For stability of any system, it is mandatory to del, uh, change into the load angle with respect to time should be 0. If your system is stable, then this point should be satisfied. So for a stable system, following conditions should be satisfied, and it is clear from the figure. And it can be obtained through the equation, uh, through this equation. So now multiplying the equation number 29, if we multiply the equation number 29 uh, with 2d delta upon dt, then we will get the equation number 30. Now integrate with respect to time. If we integrate the equation number 30 with respect to time, then we can obtain d delta upon dt square is equal to 2 by m integration delta 0 to delta, means the full load angle we have to cover here, pa d delta, which is equation number 31. So it is known that the accelerating power is equal to pa is equal to pi minus pa. The difference between the mechanical power input to the generator and the generated electrical power is known as accelerated power. If initial power angle before disturbance is theta naught, then as per stability criteria, d delta upon dt is equal to 0 at some moment, which implies that integration over delta 0 to delta pa d delta is equal to 0. Equation number 32. So the equation 32 indicates that the average area under the graph between pa and delta must be 0 for the sum value of delta for for stability. So which is represented in a next figure. So in a positive, so if we plot again uh, means load angle versus power curve, so we will get this power angle characteristics of a synchronous generator, where pe is equal to p max e sin delta, which is this point where the maximum power is obtained, and the angle is the load angle here. So now Initially, Pi is equal to 0 is equal to Pe0 at point A. Let us assume here a point A, and initially Pi0 mechanical power is equal to electrical power at point A. So now suppose sudden change in Pi and Pa will be positive and rotor moves to point A. Suppose if sudden change in Pi due because of any reason the mechanical power is changed on the shaft, then the corresponding Pa will be changed and it will be a positive. So rotor moves to the point A to point number B here, point number B. So your motor will be means the power generated from the generator means electrical power will be goes up to the value of Pi0 to Pia Pi, and the point is what, this point B. So power will be changing this nature means power increases due because of sudden change in it. So it's a step behavior of a rotor, and the power goes from A to B. Corresponding load angles are delta 0 and delta 1. So consequently rotor accelerate and delta increases. Now at point B, Pi is equal to Pe and delta is equal to delta 1. Then d delta upon dt is positive and point B will be final steady state operating. So point B will be considered as a final steady state operating point for the machine. But however, the acceleration is positive, so rotor will be shooted here and it will be goes up to the value of C. So your corresponding load angle is change delta 2 and the corresponding point C is the generated power is C. So now if we consider it as a machine is at its maximum generated power output, so it will be considered as the maximum load angle, and the again rotor swing back to the point B because point B will be considered as the next operating point from A to B. Now due because of acceleration it will be goes up to the C. So it is again deaccelerate and come to the point number B to get the settle here. So at point P, B, Pi is equal to Pe and delta is equal to delta 1 d delta upon dt is positive, and the point B will be the final steady state point and it's overshoot towards the C. Now Pa is negative because it is goes down. So Pa is negative means it is deaccelerated, and delta is equal to delta 2 reaches its maximum point C and then swing back to point B. This is the final steady state operating. So, so on the basis of this analysis, we can say then according to the following equation, because PA means the total area enclosed during in a curve in a positive or in a negative means during the acceleration and deceleration it will be equal. So the integration over delta 0 to delta 2 PAD delta should be 0 for stability. So we can say that the area A1 is equal to area 2. Here you should remember one thing. Here we have to assume that the machine is connected to a large system. So the VI and XG means the voltage and the reactance, synchronous reactance of the machine is not changing due because of changing to the PI, and it is maintained constant current with constant EG. So because VI and XG is not changed, so we can assume that the your it maintains a constant field current, so field doesn't change and with a constant Eg. So this is just a point. Here we have to assume that, but in actual practical system, whenever your sudden mechanical change is applied on a rotor shaft, then corresponding excitation level is also